In this video, we explore transformers under loaded conditions. But before we proceed with the proper discussion, let me discuss transformer dot convention. So this convention is used to identify the polarity of the secondary terminals with respect to the polarity of the primary terminals. On the left drawing, um, we mark the primary and secondary windings with dots. Okay. So these these two dots means that if I apply a voltage at the primary V sub 1 with this polarity, the voltage that will appear at the secondary will have a polarity that is positive at the dot and negative on the other terminal. On the other hand, if the dot is shown to be like this, if I apply voltage at the primary with this polarity, the voltage at the secondary will appear with a polarity where the positive terminal is at the bottom, or where the dot is, and the negative will be on this terminal. So the dot convention tells us what is the polarity of the secondary winding with respect to the polarity of the primary winding. Let's proceed with our discussion on the characteristics of a transformer under load conditions. So here we assume a perfect two-winding transformer. So when we say perfect, that would be an ideal transformer. So an ideal transformer has the following attributes. We have zero core loss. The magnetic permeability inside the core is very high, and the reluctance of the magnetic circuit is approximately zero. So reluctance is like resistance, but it resists the flow of flux inside the magnetic core. An ideal transformer has zero resistance at the primary winding and a zero leakage flux at the primary side. So because we have zero core loss, that means our I sub C would be zero, and that would mean our exciting current is simply equals to the magnetizing current. So the flux formed in the magnetic circuit, we know that to be dictated by the applied voltage and is formed by the product of the number of turns in the primary winding and the magnetizing current. We call that magnetomotive force, or MMF, due to the primary winding. So as you can see, the flux is really due to two factors, and that is the number of turns in the primary winding and the magnetizing current. Based on Ampere's law, the MMF produced by the primary winding will be equal to the sum of the MMF drops around the magnetic circuit, and that will result into an equation that looks like this. That is, the MMF will be equals to the product of the magnetic flux times the reluctance of the magnetic circuit. Now, since the reluctance is zero, because we're talking about ideal transformers, that means to form the flux inside the core, the needed MMF is almost negligible. By Faraday's law, we can determine the induced voltage at the primary winding And since the same flux uh, produced by the primary winding links to the other winding at the secondary, that means that the secondary induced voltage is given by this, where it is proportional to the number of turns of the secondary winding, and that would also be equals to the terminal voltage at the secondary winding. If we divide this equation with this equation, that will give us this, which is really the relationship that we have uh, for an ideal transformer when it comes to the ratio of the voltages at the primary and secondary windings, uh, which is equals to the turns ratio. Let's say we connect the secondary winding to the load, and let's see how the transformer reacts. So the first thing that will happen if a load is connected to the secondary is that, well, the secondary will supply current because take note that there is a voltage across the secondary. Now this current um, will combine with the number of turns n sub 2 to form uh, an MMF n sub 2 I sub 2. This MMF will produce a flux inside the core. Okay, so a flux will be produced inside the core due to this MMF, which is opposite to the flux that is already there, that was produced by this MMF coming from the primary winding. Now, these flux produced due to I sub 2 will be in opposite direction of the original flux, and therefore this MMF produced by I sub 2 is called a demagnetizing MMF because it tends to lessen the flux inside the core. Now, uh, since we're talking about ideal transformer, we know that the reluctance is zero, so there's no reluctance that will limit the existence of the flux inside. We also know that the core flux is just dependent on V sub 1, which is a constant. So therefore, we can say that the total flux inside the core must be a constant. So originally, we have this flux here produced by n sub I sub m, but we said that it is decreased due to the demagnetizing component or the demagnetizing MMF due to I sub 2. So how are we going to maintain the flux inside the constant value? Well, what happens there is uh, when the load draws a current I sub 2, the primary winding immediately draws additional current, called that current I sub 2 prime. Okay, uh, okay, there you are. So the primary winding will draw additional current in order to produce additional MMF to counter the demagnetizing MMF that was produced by uh, the current drawn by the load. Now, that additional flux will counter the flux produced by N2I2 in order to maintain the flux inside the core. Okay, so by that we can say that every time a current is drawn by the load, a corresponding current, well, it may not be exactly the same depending on the turns ratio, additional current is drawn. So if we draw more current on the secondary, additional current will be drawn by the primary to counter the flux due to this demagnetizing um, MMF. Uh, in a similar manner, if the current drawn by the load decreases, the current that will be drawn by um, the primary will also decrease. So here it is what is happening. So originally we have N sub 1 I sub m to form the flux inside the core. The load draws a current I sub 2. Therefore, it forms a demagnetizing MMF that is opposite to the uh, this MMF. That is the flux that is produced by these two MMFs are opposing each other. But since the flux is a constant, the primary winding or the transformer would draw additional current that is to add to this original MMF and to maintain the equilibrium of the flux inside the core. So that means these two terms here must be a zero, or they are equal in magnitude in order for the main flux inside the core maintain to a constant value. So we then have this relationship that the MMF formed by the secondary current N2I2 is equal to the additional MMF formed in the primary. Now, we know that the total primary current is the combination of the magnetizing current and the additional current due to the secondary winding current. So therefore, we can replace this here by this one. So let's replace that, and that will give us this relationship, which can be simplified into that expression. Uh, However, since we said that this is very small, so therefore we can approximate this to be equals to zero, and that will simplify this equation into this equation. And if we rearrange it, the ratio of the primary current over the secondary current is equals to the reciprocal of the turns ratio, which is again true for ideal transformer. Let's say our secondary load is a simple impedance Z sub 2, and we're asked to find what are the currents I sub 1 and I sub 2, and also the voltage V sub 2, given that we apply voltage at the primary side. Well, what we can do here is we transfer this impedance at the primary, so that will give us this. Uh, so if we transfer that impedance to the primary, that impedance will look different with respect to the primary. In fact, it would look like this. So this is equals to Z sub 2 H squared. And we can replace Z sub 2 here by short circuit. Okay. This whole thing here we could also replace, since this is a short circuit, we can assume this to be a resistance that is equals to zero. And if we transfer this on the other side, it will also give us a zero value. And therefore, the circuit further simplifies to the circuit. So this now becomes the equivalent circuit of the transformer with respect to the primary side. Let's have an example to show how to get the parameters of a transformer. So let's say we have here a step-down transformer where the ratio n sub 1 over n sub 2 is equals to 14. That is, we have a turns ratio of 14. It is also given here that the secondary winding has a resistance and a reactance, and the resistance here is 0.05 ohms, while this is J 0.97 ohms. Take note that the reactance is a consequence of the leakage flux that is present on the secondary winding when the transformer is or the transformer secondary is connected to a load and it draws a current. So the question here is we are required to draw the equivalent circuit of this transformer with the series impedance. So this is the series impedance at the secondary referred to the primary side. Okay, so that means we'll be transferring or reflecting this impedance to the primary side. Also in question B, the primary is connected to the primary while the secondary terminals AB is shorted. So we're required to determine what is the resulting current both in the primary and secondary windings. Here's the original circuit again, and in order to answer the first question, we need to transfer this impedance here to the primary. So we draw the equivalent circuit. So this is our primary here, and we transfer the resistance and the reactance, and okay, so that will be the result, where this is 0.05 times 14 squared, and this is J 0.97 times 14 squared. Okay, so take note that in reality there is an ideal transformer here. Okay, however, the secondary is an open circuit, so we can simply ignore this part here. So there's no current here. Okay, and therefore there's no current here. This is also zero. And since I sub 1 is a 0, that means this is an open circuit, and therefore we can draw the circuit like this. Okay, where this is 9.8 ohms. Okay, so this is 9.8, and this one is J 190.12 ohms. Okay, so this is B sub 1, B sub 1 here. Okay, so this is the equivalent circuit of the transformer referred to the primaries. Okay, so this is the equivalent circuit referred to primary side. Now, to answer the question for letter B, so the second question tells us that we apply a voltage at the primary winding equals to 120 volts RMS, and we short the terminals AB at the secondary. So the question is, what is this, and what's this, and also this one. So we call this the short circuit current, because that is also the current here. Okay. Now we need to, or we can use the equivalent circuit to answer this question. Now, if you short out the terminals AB, the equivalent circuit uh, would look like this, where this is 9.8 ohms, and this is J190.12 ohms. Okay, so we also have a short here, because what really happens is, okay, we have, if we put here a transformer, an ideal transformer, this part here is also shorted. Okay, so this is like a we can assume this to be a resistance which is equals to 0, and if we translate this on the other side, that means that it should look like this. Okay, so this is V1. Okay, so this is a simple circuit that we can get I sub 1 here. So I sub 1 there would be equals to 120 divided by 9.8 J190.12, and that will give us an I sub 1 of 0.63 with a phase angle of 57 degrees. Okay. And since we know that I sub 1 over I sub 2 is equals to 1 over A, we can compute for I sub 2, and that will give us A I sub 1, which is equals to 8.82 with the same phase angle as I sub 1. We can also compute for V sub 2, which is the voltage across the secondary winding, and that is equals to, based on the original circuit, that would be 0.05 J97 times I sub 2. And that should give us 8.57 angle 0. So the voltage V sub 2 has the same phase as V sub 1, which we assume to be 0 degrees. In our next video, we'll be discussing more about the equivalent circuit of a transformer. In that discussion, we'll develop a more complete model of a transformer.